Data privacy mandates often prohibit sending proprietary documents to external large language model providers. The solution requires a fully contained local retrieval-augmented generation architecture. This system relies on three core components: LangChain for orchestration, ChromaDB for persistent vector storage, and Ollama for managing both the embedding model and the generative large language model. We are targeting sub-second query latency on commodity hardware. The initial setup requires Python 3.10 or higher, installing the LangChain core, LangChain community, ChromaDB, and the specific document loaders needed for your data source, typically PDF or Markdown. Ensure Ollama is running locally on port 11434 before proceeding, as this serves both the embedding and generation endpoints. Effective retrieval-augmented generation performance hinges on intelligent document segmentation. We utilize the recursive character text splitter, which preserves semantic context better than simple fixed-size splitting. For technical documentation, set the chunk size to 1,000 tokens with an overlap of 200 tokens. This overlap ensures that context is maintained across chunk boundaries, preventing critical information from being split in half. Load documents using the directory loader, specifying the file type, for example, unstructured Markdown loader for technical specifications. The resulting list of document chunks, each containing metadata including the source file path, is the input for the embedding process. The choice of embedding model directly impacts retrieval quality and system resource consumption. For local deployment, models optimized for speed and accuracy are essential. We select Nomic Embed, specifically the 8192 dimension version, which offers superior performance compared to older sentence transformer models while remaining manageable locally. Pull this model using the Ollama command line interface, Ollama pull nomic-embed-text. Configure LangChain's Ollama embeddings class, specifying the model name nomic-embed-text. This ensures that all document chunks are converted into high-quality, dense vectors, ready for indexing in the vector store. ChromaDB provides a lightweight file-based vector store suitable for local RAG systems, eliminating the need for external database dependencies. Initialize the Chroma client, pointing it to a local persistence directory, for example, //ChromaData. Define a unique collection name, such as project specifications. Pass the list of document chunks and the configured Ollama embeddings instance to the chroma.fromDocuments method. This step performs the vectorization of all chunks and indexes them for rapid similarity search. The persistence directory now contains the complete vector index, allowing the system to restart without re-embedding the entire corpus. The vector store object is converted into a retriever instance, which handles the query to vector conversion and similarity search. Set the search type to similarity and the k parameter to 4. A k value of 4 means the retriever fetches the 4 most relevant document chunks based on the user's query vector. For complex or diverse document sets, consider using maximum marginal relevance search instead of pure similarity. Maximum marginal relevance prioritizes documents that are both highly relevant and diverse, reducing redundancy in the context passed to the large language model. This prevents the model from receiving 4 nearly identical paragraphs, improving generation quality. The generation step uses a local large language model managed by Ollama. We select Llama 3 8B Instruct for its strong reasoning capabilities and efficient local footprint. Configure the LangChain Ollama class, specifying the model name Llama 3 and setting the temperature parameter to 0.1. A low temperature is critical for factual retrieval-augmented generation tasks, minimizing creative or speculative outputs. Ensure the system prompt is clearly defined within the prompt template, instructing the model to use only the provided context for its answer, and to cite the source document metadata if possible. The prompt template structures the input for the large language model, combining the user query and the retrieved context. Use a chat prompt template with a system message and a human message. The system message must explicitly state the model's role. You are an expert system analyst. Answer the user's question strictly on the following context. If the answer is not found, state that the information is unavailable in the provided documents. The human message template includes placeholders for the context, which is the retrieved documents, and the question. Proper prompt engineering prevents the model from relying on its internal knowledge base, enforcing adherence to the local data. LangChain Expression Language provides a declarative way to chain components, ensuring efficient data flow. The pipeline starts with the user query. This query is passed to the retriever, which outputs the list of documents. We use a runnable parallel map to structure the input for the prompt. Context maps to the retrieved documents, and question maps to the original input. The chain sequence is input/retriever/runnable parallel/prompt/model/s output parser. This structure guarantees that the retrieved context is correctly formatted and inserted into the prompt before reaching the Llama 3 model for final generation. Execute the final chain by invoking it with a test query. For example, what are the security requirements for the new authentication module? Crucially, implement a validation step by inspecting the output of the retriever before the generation step. This is achieved by adding a simple logging function after the retriever in the chain. Verify that the 4 retrieved document chunks are logically relevant to the query. If the retrieved documents are irrelevant, the embedding model or chunking strategy needs adjustment. Successful execution confirms the local RAG system is operational, providing accurate, source-grounded answers without external dependencies.